Exercise 10.12. This is on page 420 from the book. That is 10.6, I believe. So if you're online, this would be 10.5, 10.6 scanned pages with the notes. And if you're not online and you're a hybrid, then you should have page 420 in your book. So sample of the KCl03 is partially decomposed. The equation is 10.6, so let me just put that equation up here for you so you can see it. The equation, there we go, is KClO3, that's a solid, and then KCl, that looks ugly, don't move. Yeah, okay, let's lock that in. There, now I don't have to worry about it moving. Cl, that's also a solid, plus O2, and that's a gas. Now, for this equation, we're going to have to balance this. So the balanced product is a 2 KClO3, 2 KCl, and 3 oxygens. Okay, that ends up being important later on when we're talking about B and C. So, or just B. This says the volume of gas collected over the water, as in figure 1016, that would be this figure right here. We have KClO3 right here being heated. Oxygen gas is given off. It goes through the tube, and then this is how it gets collected. So this beaker right here was flipped upside down with water in it so that there is no other gas other than O2 that's collecting at the top here. The problem is, the reason why you would collect gas over water is so that there would be no chance for other gas to get in. The only thing you have to account for is the fact that there is a pressure from the amount of water vapor that evaporates from the surface of the water inside the beaker. So the total pressure here is just simply whatever the pressure of the gas is plus the pressure of water. So all we have to do then is look to see what the temperature is of the water that's inside, and then that will tell us what the vapor pressure is using this chart. You can use Appendix B in the back if you have a book, or you can use this chart. In the problem here, I'm going to flip back. In the problem here, it says there's 26 degrees Celsius is my temperature. So when I flip forward to this chart here, 26 is 25.2 millimeters of mercury. And that's the value we're going to use then to solve this problem. So I know I'm throwing a lot at you at the time, like all at one time, but it says the volume of gas collected is 0.25 liters at 26 degrees Celsius at 760 torr total pressure. So that would be total pressure equals 765 torr, which is the same as millimeters of mercury. So what do I do? Total pressure equals pressure of the gas, which is O2, plus the pressure of water, which is H2O. So if I want to know what the pressure of O2 is, because that's the whole point of this problem, is to find the number of moles of O2 that's been collected, then my pressure of O2 then is going to equal the total pressure minus the pressure of water, like that. Okay, that ends up being pretty easy. So what I do is I take the total pressure of 765 torr, and I subtract what I got before, which is 25.2 torr, and I'm going to just simply round off then. My pressure of oxygen is going to be 740 torr, and that's the pressure, that equals the pressure of just O2, like that. Okay, now once we get that, once we know what the pressure of just the oxygen by subtracting the water vapor, it says how many moles. So that means if I'm talking about PV equals nRT, what I'm going to be solving for then will be the pressure of O2. So that will be 740 torr. The volume is given to us as 0.25 liters, 0.250 liters. with significant figures. That's what we're looking for. If I have torr, my R value then is 62.4. You know what that is? That's torr times liters. When I have degrees Celsius, as in 26 degrees Celsius, I simply add that to 273, and whatever I get there then is going to be my temperature, like that. So PV equals nRT, N equals PV divided by RT. I'm just going to simply plug in the stuff that we have. 740 is my new pressure. Volume is 0.250 liters. All of that is over R, which is 62.4, and then 299 Kelvin, like that. And what I'm going to be left with then is going to be moles of O2, like that. So when I do my calculator, I'm going to walk over and get my calculator. Okay, so it looks like it's going to be 740 times 0.25 divided by 62.4 divided by 299, and that equals 0.000, so 2 zeros, 0.00992 moles of O2. Okay, so that's the number of moles that we produced. The question then is for letter B, which I'm going to do in green. The question is for letter B. All of that was letter A, so I'm going to do letter A up here. In letter B, it says how many grams of KClO3 were decomposed. Well, I'm going to start off with the number of moles that I have. That's 992 moles of O2. All of that over 1, and then I'm going to do a mole-to-mole conversion using, and I have to scroll up for this, using number of moles of oxygen for the number of moles of KClO3. So it's a 3:2 ratio, which means that if I'm talking about, let me just start over with this. If I'm talking about number of moles of KClO3 like this, that would be 2 moles for every 3 moles of O2, like that. That says moles, M, there. Good. So once I make this calculation, I'm going to multiply by 2, divide by 3, and I get the number of, that's going to equal here. I'm going to have to scroll down, get myself a little bit more room. So this is the number of moles I got of KClO3. That's not what it's asking for, though. It's asking for the number of grams. So the question is, what is the number of grams per 1 mole? So the number of grams per 1 mole would be 39.1 for potassium plus 35.5 plus 48. All these added up give me a second to do the plus 35.5 plus 48. Okay, equals. So it looks like, what is that? That's like 100, shoot, it didn't tell me what it was. All right, I'm going to write this part down first. I got 0.810 grams. And it didn't tell me what it was. 39.1 plus 35.5 plus 48 equals 122. So that would be 122.5 grams for every 1 mole. The 122 is what I get with the 1 potassium, 1 chlorine, and 3 oxygen. 3 oxygen is 48, because 16 times 3. And then 122.5 is the number of grams I get for the whole KCl thing. So when I multiply these going straight across, I get 0.810 grams of KClO3. And that's how you do that problem. Super easy, huh? Here's what it looks like. And then here is the 25.2, which I just rounded off to 25. Good.